In this lesson, I'll talk about some theorems concerning open and closed sets for topological spaces. If you looked at the videos I prepared on metric spaces, you'll notice these results are quite similar, but keep in mind that every metric space is a topological space, but not the other way around. So we have one exception that I prepared an example for, where we have a result that holds for a metric space, but not for topological spaces. I have a few definitions to get started. The subset Y of a topological space, X tal, is a neighborhood of a point X if there is an open set U such that X is an element of U and U is a subset of Y. So we have a general picture of it here. So we have X in a open set that includes X, and then we have some set Y in which U is a subset of. And in this case, that we say that Y is a neighborhood of X. So notice the key point here is that Y doesn't need to be open. This could be a closed set. It could be a set that's neither open nor closed. It could be a set that's both open and closed. And it could still be a neighborhood of X as long as it contains, it meaning Y, contains a subset, an open subset U that contains X. So that's neighborhood. So it's a little bit complicated because of the misdirection here, but that's how it's defined. Then a point X in our metric space, capital X, is an interior point of Y. If Y is a neighborhood of X, the set of interior, so that's what we just discussed here. The set of interior points of Y is called the interior of Y and is written int Y. And clearly the interior of Y is a subset of Y. So we again have one example here. So Y may be a closed set, for example, but it would still have an interior, and it just wouldn't include the boundary in this case. So actually, we'll talk about the definition of a boundary at the very end of this lesson, but you can kind of get a general idea here from what I've drawn that if you think of just two-dimensional space, this could be a kind of a squiggly shaped closed set, and it has an interior that's everything except for its boundary. This theorem should look familiar from metric spaces. We have a subset of a topological space is open if and only if the subset Y equals its interior. So as we mentioned on the previous slide, we always have that the interior of a subset of a topological space is a subset of the space itself. So interior Y is a subset of Y. Let's prove the theorem going in the forward direction. So assume Y is open. Then for every Y, an element of Y, Y itself is an open set containing Y. Thus, every Y, an element of Y, is an interior point, which implies that Y is a subset of the interior of Y. So between this result here and this result here, we conclude that Y equals its interior. Going in the other direction, assume that Y equals its interior. Then for each small y, an element of Y, there exists an open neighborhood U sub Y, this is by definition, of Y, neighborhood of Y, such that U sub Y is a subset of Y. The union of all U sub Y's is open. That's just the definition of topological spaces. Any union is again an open set. And thus we have that the union, this here is union over all Y, an element of Y, of these sets, U sub Y equals Y itself. Since U sub Y is a subset of Y, and every Y is in one of these U sub Y's. So thus Y is open. If Y is a subset of a topological space, X, with topology tal, then the interior of y equals the interior of y. That may seem obvious, and you may recall that we had this very same statement for metric spaces. So let's look at a proof. As we mentioned before, the interior of any set is a subset of the interior of the set. So for what we're talking about here, we have the interior of y is a subset of the interior of y. We just need to show going in the opposite direction to show that these two are equal. So take any y in the interior of capital Y. By definition, there's an open neighborhood U of y such that U is a subset of y. But since U is an open neighborhood of each of its points, U is a subset of the interior of y. Thus, y is an interior point of the interior of y, i.e. I is an element of the interior of y, which implies that the interior of y is a subset of the interior of y. And these two statements together imply that the interior of y equals its interior. As we saw in the last couple of theorems and also in these definitions on this slide, which we'll get to in a second, we have a lot of parallels to the metric spaces for topological spaces. And this kind of goes back to what I said in the last lecture, that we could have done topological spaces first and then just showed metric spaces as a special case, and noted that there were some exceptions where you had things that held for metric spaces but not for topological spaces. Okay, so let's look at a definition here of adherent. Given a topological space X with topology tau, a point X in capital X, the metric space, is adherent to a subset Y of X if every neighborhood of X intersects Y. Each point of Y is then adherent to Y. And in addition to that, you could also have points that are on the boundary of Y. So in other words, not in Y, but every neighborhood surrounding that point intersects Y. And those would also be adherent points. And again, we saw something very similar with the metric spaces. The closure of Y, written as Y bar, is the set of points in X, our metric space, which are adherent to Y. Clearly, Y is a subset of its closure, and we'll see in a minute that if you have a closed set, then Y needs to equal its closure. We have a theorem here that's exactly the same as what we had for metric spaces, but now we're proving it in a more general setting of topological spaces. The subset Y of a topological space X is closed if and only if Y equals its closure. As we noted in the previous slide, Y is always a subset of its closure, independent of whether or not Y is closed. So we'll use this in our proof here. First, we'll prove if Y is closed, then Y equals its closure. So assume Y is closed. By definition, its complement is open. And since Y complement is open, every point in the complement of Y is an interior point. And so no point of the complement of Y is adherent to Y, meaning that all of the points adherent to Y, in other words, all the points in its closure, have to actually be inside of Y. So we have this here, and then this statement here and this statement here together imply that the closure of Y equals Y. Then going in the other direction, assume that Y closure equals Y, and take any X in the complement of Y. And since we have this equality here, we know that X is also not an element of the closure Y. So there exists a neighborhood U sub X of X for every X in the complement of Y, such that U sub X intersected with Y is empty. In other words, U of sub X is a subset of the complement of Y. Then we take the union of all these U sub X, And since every x in our complement of y is in one of these, and each u sub x is a subset of y complement, then we know that the union of all these is equal to the complement of y. And since the union of open sets is open, the complement of y is open, and thus y is closed. So that proves the theorem in the opposite direction. We have another theorem that's exactly the same as what we had for metric spaces. If y is a subset of a topological space, then y closure is closed. In other words, the closure of y equals the closure of y. So let's prove that. If x is an element of the complement of the closure of y, then there exists an open neighborhood u sub x of x that does not intersect y. In other words, u sub x intersection y equals the empty set. And since u sub x is a neighborhood of each of its points, no point of u sub x is adherent to y. So that means u sub x is a subset of the complement of the closure of y. And then we take the union of all the u sub x sets, and that would equal the entire complement of the closure of y. So the complement of the closure of y is open, being the union of open sets. That's from the definition of a topology. And by definition, its complement, the closure of y, is closed. So in other words, if the closure of y is closed, then it equals its closure, which is this double bar, y double bar. Even though we don't have a metric or a distance function for topological spaces, we can define convergence of a sequence using open sets, and I have that definition here. Given a topological space X, a sequence of points x sub I converges to x, little x, an element of our topological space, if for every open neighborhood u of x there is an integer n such that x sub I is an element of u for every I greater than n. And I should have said positive integer. We have a theorem. Given a subset y of a topological space, if a sequence y sub I and y converges to little y, then little y is an element of the closure of y. The proof is pretty short. By the theorem from the previous page, we know that the closure of y is closed, so its complement is open. And since little y sub I is an external to the complement of the closure of y, the sequence little y sub I cannot converge to any point of the complement of the closure of y. Therefore, since we know that it does converge to y, that y must be in something other than the complement of the closure of y. In other words, it must be in the closure of y. So that proves the theorem. The converse of this theorem is not necessarily true for topological spaces. It is true for metric spaces. We prove that in theorem 69. Here's the converse, the statement of the converse. If y is an element of y closure, then there exists a sequence y sub I in capital Y that converges to y. So that would seem obvious from all our work in metric spaces, but I'll show you a counterexample where that doesn't work for at least one type of topology. And that'll take several slides to develop, but we'll do that in this lesson. We're going to talk about the co-countable topology, and eventually we'll show this is a counterexample to the converse of the theorem from the previous slide. But first we need to define it, and then we need to show that it's actually a topology, and then we'll get to the counterexample. So let X be a set with topology tau consisting of the collection of subsets U such that the complement of U is at most countable. So in other words, finite or countable to get along with the empty set. So that's our topology on a given set X. And this is known as the co-countable topology. And I gave a reference here, and I also, this is from my book, which you can download freely. And I also gave the reference directly down here. So for example, if we take our set X to be the real numbers, and we let I represent the irrational numbers, the set I is open under the co-countable topology on R, since the complement of I is countable, right? The complement of the irrationals is the rational numbers, and that's countable. Let's take another example. If we take V sub 0 to be just a set with 0 in it, and then U sub 0 equals the complement of R, the complement of V sub 0 in the real numbers. In other words, the real numbers with 0 removed. Then this U sub 0 is an open set, since its complement is finite. So a little bit of misdirection here. You need to think twice when you read some of these examples. But what we want to do next is show that this is a topology. So we'll do that in the next slide or two. That co-countable is a valid topology. We're given that the empty set is in the topology, and the entire space is also in the topology because the complement of X is just the empty set. So we have that. Next, let's look at the unions. Take any collection of elements from tau, U sub A, where A is an index, capital A is an indexing set, potentially uncountable. By De Morgan's laws for sets, the complement of the union of these open sets equals the intersection of the individual sets. And this right side here is clearly most countable because it's the intersection of these sets which were at most countable. So when you intersect, you get something smaller. So the right side is at most countable, which means that this union of sets, the complement of the union of these U sub A's is at most countable, which means that the union of the U sub A's is also in our topology tau. Okay, then the last part in showing that our countable definition is a topology is to show that finite intersections are also in our topology. So take any finite collection of elements from tau, we'll call it U sub B, where capital B is a finite indexing set. Then again, using De Morgan's laws, we have that the complement of the intersection equals the union of these complements. And the right side is at most countable, since it's just the union of a finite collection of at most countable sets. So this is at most countable, which means that the complement of the intersection is at most countable, which means that the intersection itself is in our topology. So we've now shown that co-countable is a valid topology. Now we're ready to do our counter example. I want to talk about convergent sequences in the co-countable topology. We have a theorem. The only convergent sequences in X, tau, where tau is our co-countable topology, are those that eventually become constant. So let's prove that. Let X sub n be a convergent sequence in X, and little x be its limit. In addition, let U equal X minus all the terms in the sequence that don't equal X. So I have a picture here that's just sort of a high level concept of what we're talking about here. But of course, topologies are not just two-dimensional space, so this is not an actual depiction of what's being expressed here, but just sort of an aid to help visualize. So U is everything in X, including the point little x. In other words, all the points in the sequence that equal little x, which may not be any of these sequences. It's possible that this sequence doesn't ever actually equal x; it just converges on it. But U is this set here, x, and everything else in our topological space, except for these points here in the sequence that don't equal x, and that's U minus x, the complement of U. So that's what I'm expressing up here. In other words, and just writing it down, U is all of x except for elements in the sequence x sub n that do not equal x. So that's just what I've illustrated down here. So x is an element of U. Since x, the complement of U equals xn not equal to x, in other words, these guys in here, is it most countable? So that's clearly the case because all sequences are numbered by the integers, positive integers, so they're countable. And if you take a subset, you're still just a countable set, or even a finite set. Okay, so since the complement of U is countable, and U is in our co-countable topology. That was just a definition of co-countable, which means that U is an open set, right? Anything in our topology is by definition an open set. Since U is open, and X is an element of U, and X, the sequence X sub n converges to X, it must be that X sub n is an element of U. All X sub n are an element of U for some n, an integer n, a positive integer n, and all n, little n, greater than n. That's by the definition of convergence, which I recopied down here from previous slide. So, however, X sub n is an element of U for every n greater than n, what we just set up here. It means that given the way we've defined U, X sub n must equal X for every n greater than or equal to this n. So in other words, X sub n eventually becomes constant. At some point, all these members of our sequence have to equal X. So we've proven, almost proven the theorem. We have one more part to prove, which I'll prove on the next slide. That's kind of trivial, but we need to state that. I have one bit more to prove, which may seem trivial, but I'll go through it in any event. Well, on the other hand, if X sub n eventually becomes constant, in other words, X sub n equals X for all n greater than n for some n in the natural numbers, in other words, the whole numbers, positive whole numbers. In this case, any neighborhood of X will eventually contain X sub n for n greater than some capital M, where M is again a natural number. M could be less than this n up here, which implies by our definition of convergence that X sub n converges to X. So this is just a matter of showing that if you have a sequence that's eventually constant, it fits the definition of convergence. So the all convergent sequences in this co-countable topology eventually become constant. We're going to use that for our counter example. Well, finally we got to our counter example of the converse of theorem 95, which I've written down here. If little y is an element of y closure, then there exists a sequence y sub I and y that converges to y. So we're going to show this is not necessarily true for topological spaces via a counter example. So first we're going to note what are the closed sets in the co-countable topology. And we know that the empty set and the set itself, X, are both open and closed in all topologies. So we have that. We just need to show that the only other closed sets are the most countable sets, or sets which are at most countable. So let V be any at most countable set in X. We let U equal the complement of V. Then we have that the complement of U is the complement of V, which is V, which implies U is open, since that's by definition, right? If you any set which is whose complement is at most countable is open, so that means U is open. And then by the definition of open and closed in a topological space, we know that V is closed since it's the complement of U. So any at most countable set in X is closed. Now, we need to show that any uncountable set in X is not closed. So let U be any uncountable set in X. Let V equal the complement of U. Then we take the complement of V. So it's the complement of U, and that gives us U, which implies V is not open. Right? For V to be open, its complement would need to be at most countable. We see its complement is uncountable. Its complement is U. And that implies that U cannot be closed, because if U is closed, then its complement V would be open. So we have that U is not closed. And in other words, no uncountable set in X is closed, and that leaves us with the only closed sets in X being those that are at most countable. Okay, now for the counterexample. So let A equal the singleton set Y. And from the above, we know that A is closed, right? It's at most countable, so it's closed. And thus B equal being the complement of A is open. So this set B is open. It must be that the closure of B equals all of X, since there is no other closed set that can contain the open set B. Okay, so consequently the closure of B contains the point Y. That's the only other point in X other than what we already have in B. But Y cannot be the limit of a sequence in the set B. And that contradicts what we have down here as the converse of theorem 95. So maybe a little bit of explanation as to why this last statement is true, which I put down here. So let Y be an element of the closure of B. We know that, right? We already have that. And let Y be the limit of a sequence Y sub I in open set B. So we're kind of taking this part of the theorem here. So let that be the case. Then by the definition of convergence, for every open neighborhood of Y, B in this case, there exists an integer n such that Y sub I is an element of B for all I greater than n. However, for the topology at hand, we know that all the convergent sequences eventually equal the limit, which implies Y is an element of B. But we already defined B to be the complement of A, so Y is not in B. Thus we have a contradiction, and Y is not the limit of a sequence in B. So that's further explanation of our counterexample here. So a lot of work just to make the point that not everything that works for metric spaces holds true for topological spaces. Now, granted, this is a bit of a contrived example. It wasn't my creation, but someone created this as a counterexample, and I just re-explained it here. So I'll give you a little bit more of a specific example in the next slide. It may help understand this a little bit better. So here's the example I mentioned on the previous slide that may help. I was a bit confused myself when I first saw the co-countable example, and I was wondering, well, if we apply the co-countable topology to R, why, for example, doesn't the sequence 1 over n converge? We know it converges in regular Euclidean space and converges to 0. And the problem is we violate the definition of convergence in this example here. Let A equal the sequence 1 over n for all the different terms. And then since A is at most, well, it's countable, so that means it's the complement of A is B, called B. Complement of A is a at most countable set, in which case B is open, and that's the problem. B contains 0, the limit of this, but it contains no elements from A. Thus, by definition, the sequence 1 over n does not converge. Remember, the definition was a sequence of points converges to x, which would be, our sequence would be 1 over n, and x would be the 0, for every open neighborhood U of x. So B is an open neighborhood of 0. There is an integer n such that x sub I is an element of U for every I greater than some n, but that's not the case here because B is the complement of A, so we have a contradiction. So it's a kind of a convoluted example, but it violates this definition, which is, what people have agreed to as being the definition of convergence in a topological space. I'm sure they considered other examples, but this is what they'd come up with, I'm sure, after a lot of discussion. If you recall from the beginning of this lesson, I talked about boundary points and the boundary of a subset, but I didn't give a formal definition. So we'll do that here, and we also have a theorem. A point B is a boundary point of a subset, capital Y, of a topological space Y if B is adherent to Y and to the complement of Y. And we write that as this delta Y. And more formally, we have this definition here. The boundary of Y equals the intersection of the closure of Y and the closure of the complement of Y, which basically is saying you're adherent to both Y and its complement. So this statement and this equality here are the same. Clearly, the boundary of the complement and the boundary of the set itself are the same. It's just a matter of switching the order of these two things in the intersection. And the boundary of Y is closed, being the intersection of two closed sets. Of course, the boundary of the complement of Y is also closed. So we have a theorem. If Y is a subset of a topological space, then the closure of Y is the union of its boundary and its interior, where the boundary and the interior have no intersection, or an empty intersection, I should say. So let's prove that. We're going to take an element of this side of the equality and show it's in the closure of Y, and then we'll take an element of the this side of the equality and show it's in this inner union here, and then that'll prove the equality. Okay, so we'll start by taking any Y, small y, in the boundary, the union of the boundary with the intersection of Y. So if you're in the union, that means either you're in this set or in that set. So you're in one of these two. We'll look at both cases. If Y is in the interior of Y, then Y is an element of the interior. The interior, in turn, is, as we know from before, is a subset of Y, and Y is a subset of its closure. So that would imply Y is in the closure of Y, little y is in the closure of Y. And then if we have the other case where Y is in the boundary, then the Y is little y is in the closure y, since the boundary of y is a subset of the closure, right? It's in the intersection here, so it would have to be inside of both of these sets. So either way, little y is in an element of the closure y. That shows that the union of the boundary and the interior of y, is a subset of the closure y. So we've shown one way. Now we need to show taking y, an element of the little y, an element of the closure of y is in this union. So if that's the case, if y is in the closure of y, then every neighborhood u of y intersects y. That's the definition of being in the closure, right? This would have to be the case. Y is basically an adherent point. Little y is an adherent point to y. Then there are two mutually disjoint cases. Either there is a neighborhood u of y, such that u is in a subset of y, or each neighborhood u of y also intersects the complement of y. So in the former case, it occurs if and only if y is in the interior, right? If every neighborhood u of y is such that u is a subset of y, then that would imply y is necessarily in the interior of y. And in the latter case, it only occurs if y is in the boundary. In other words, because we had this here, u is every neighborhood u of y intersects y, and then if we have that it's each neighborhood u of y also intersects the boundary, the complement of y, then of course it would have to be in the boundary, because it's this, following the definition of the boundary up here. Thus, y is in the union. It's either this happens or this happens, so y is in the union, which implies that the closure of y is a subset of the union of the boundary of y with the interior of y. And I'll leave the last little bit for you to prove that the intersection of the boundary and the interior is empty. And you can figure that out just from the definitions up here.